Okay. Loose lens retinoscopy. This is one of the harder skills to learn in ophthalmology, both for you and really for me. When I was a resident doing my surgical training, it probably took a good 2 years before I really got any comfort, and I'm still getting comfortable with it. You get better with time. I thought this would be an interesting topic and a useful one because this is something you can actually use in your office. Now, I guess retinoscopy is part of your COMT certification. COT? Is it really? Okay. Do they have you do it using the manifest, the phoropter? Okay. The phoropter is a useful way. Personally, I think the loose lens retinoscopy is more useful. And the reason why is who are the patients who need retinoscopy? It's often children. And then like we already showed you, you often can't get a child up to the phoropter. And if you can do loose lens retinoscopy, you can do retinoscopy on anyone. And so I thought this is more useful. I personally don't have a retinoscopy through a phoropter. I guess I could figure it out, but I found this way a little bit easier. The difficulty with retinoscopy in general is that it is hard to teach because, one, when people describe things to you, it's very hard to visualize, especially if you've never seen it before. You get absolutely no feedback, at least with a phoropter manifesting people. They can say, I can see one better than two. With this, you get nothing. All you're looking at is the reflex in the back of the eye, and by holding different lenses in front, trying to estimate what we think the glasses prescription is based on this. So it's challenging. So here's the theory on how retinoscopy works. If you shoot a light from your instrument into the eye, and it's coming straight in, if that eye is in perfect focus, they're not nearsighted and not farsighted, they've got perfect vision, as you move your light up and down, the reflection should hit a single point on the retina, bounce back to you, and you should have a nice bright red reflex from that. Now let's say you take an eye someone's a little farsighted. Well, light coming into their eye doesn't focus right, it actually focuses behind the eye. And if you move your retinoscope up and down, the light moves up and down, and where it strikes the back of the retina, it also moves up and down in synchrony with you. When it comes back at you and you look at it, you're seeing a with reflex because the reflection is moving the same direction you're moving your instrument. If we hold a lens in front of it, not quite strong enough yet, we don't have the correct prescription, you still see a with reflection. The light beam going up and down, the reflection on the back of that retina is also moving up and down. We add a stronger lens, the correct prescription in this case, and you hit that retina perfectly, the light bounces back at you, you have a nice bright reflex, you've neutralized the reflex, this is the correct prescription for this eye. Now, if we decide to use too powerful lens, we put a very strong plus lens in front of that eye, the light actually focuses in the middle of the eye. And as you move your light, you almost get a seesaw reaction, and the reflection off the retina is actually in the opposite direction you're moving. We call this the against direction. So with versus against. Now, what does that look like in real life? Well, before we go to real life, let's look at a cartoon. This is a light beam, and your retinoscope produces a beam of light. I like to make mine nice and thin, and you can move it across the surface of the eye, up, down, left, and right, it doesn't matter. But when we look at that reflection off the retina, it moves in the same direction as you can see here. It's kind of a yellowish, orange, red color. So let's do the same experiment. We'll add a plus lens and see if we can figure out the right prescription. So let's add a +1 to the system, and we still have with motion. So it doesn't look like this lens is powerful enough. Things are still focusing behind the eye. Okay, let's get rid of this +1 and put something a little bit stronger. We'll try a +2. Now when we do a +2, the reflection is still with, it's still moving the same direction at your light beam as it plays across the surface of the eye, but you can see that the reflection has actually gotten a little bit wider back there. That's a good sign. When it gets wider like that, you're getting closer to the right prescription. Let's try +3. This is perfect. This is the right prescription to get this eye in focus. A +3 is what did it. So we've got it right on, perfectly focused on the retina. Let's go a little bit further, see what happens. +4, we're too strong now, and you can see the reflection is actually moving against us, and so that's not what we want. So that's how you do basic retinoscopy. And don't worry, I've written these steps down in your notes, and we're going to do a bunch of models ad nauseum until we figure this out. There are 3 steps to retinoscopy. The first step is you have to start with motion. If you have an eye that has against motion right at the beginning, you're going to become confused. You have to have with. The second step, you add power, like we just did, until you neutralize the reflex. And finally, at the very end, you subtract a working distance, and we'll go over that in a second. So this is a cardboard cutout I created just for this lecture to try to simulate what this looks like. I could have animated everything like that last little animation, but it was just going to take forever. So basically I used South Park techniques, cardboard cutout, and we're going to see if we can use this to figure it out. So once again, we started with width. The reflection is going with us. We add power to the system. Still not strong enough. I'm doing it in a couple different axes, and I'll explain that later. But for now, we're just looking for spherical problems. Let's try a +3. Our beam's getting wider. We're getting closer. We're almost there. So +3 is not quite that. Let's try a +4, see what happens. And +4, pretty darn close. Hard for me to estimate that perfect reflection using cardboard, but this is close. And I think we'll try a +5 just to see what happens. Let's try it. Is this too strong or not? It is, because we have against motion. And that's basically how you do retinoscopy. Not bad, not bad. Let's move on. So we ended up with a +4, got this eye in perfect focus. However, the last step, as you remember, is there is a working distance. You had to subtract -1.5 from your final spherical answer to come up with the correct one. And here's why. This is the working distance. What's that all about? Well, so far we've assumed that when light is coming into the eye, it's coming in straight from, let's say, infinity or across the room, really far away, before it focuses on the retina. But the reality is we don't sit that far away. We sit about 66 centimeters, or 2/3 of a meter, about an arm length away. Light is actually diverging a little bit before it hits the eye. And so you have to do a correction for that. And most people, this is sort of a computer reading distance, that correction is about a +150. So we subtract that from our end result to go with the answer. Now, you don't have to worry about the theory. Just realize that at the very end you have to subtract a working distance. So let's do another example. Once again, we have to start with motion. So everything's with. This is good. Let's try the other axis just to make sure everything's okay. Good. Step 1 is complete. We have width, so we can continue by adding power. Step 2, add power until you get rid of that. So we're adding power. It's getting a little bit thicker back there, a wider reflex. This is a good sign. And in every direction, good. Let's add a little bit more power, see if we've got it. A +2. And, yep, looks like we pretty much have it. All right. Let's try the other axis, make sure it's okay in that way. No astigmatism. So it looks like a +2 is probably the right lens. Let's try a +3 just to see if we can get a little bit more. And we have against, so we've gone too far. You never want against. Against is bad when it comes to retinoscopy. So we know that our answer here is what? A +2. Correct. So we'll get our lenses out, +2. And what I like to do whenever I have this situation is I don't put the lens back into the box, I put it on the counter, because otherwise you'll forget. And you do not want to be doing memorization while you're trying to do this technique. It takes enough effort to just do it. And so put it aside. And so our final answer here is a +2 sphere. But remember, the last step of retinoscopy is you have to subtract your working distance. And our final answer is this is a +0.5 diopter hyperope. All right, another example. Step 1, start with width. Good. Nice and width. All right, we're going to speed up a little bit. That's pretty good. Let's add some power. Step 2, start adding power to neutralize a reflex. It looks like we may have hit it. So let's try it. Looks pretty good. And let's set aside our lens. We don't want to lose it. And let's try adding a little bit more power, see if that helps. We add more power. Nope, we've got against motion. Let's check the other axis, make sure it's still against. It's against. And so we know that our answer here is a +1 sphere. Or at least that's what the lens that gets us in focused. So we end up with a +1. But remember, the final step, step 3, is always subtract a working distance. And you end up with a -50 sphere. Not too bad. All right. We got against motion. Uh-oh, what do we do now? Well, remember, step 1 is you have to start with motion. If you have against right from the offset, you're in trouble. So what do? You back off. Start with a -2, or -4, or -10, or whatever it takes to start with motion. If you don't start with width, you'll become very confused. So we went back to a -2. Good. Now we can add power. We'll go to a -1. That's a diopter stronger. And it looks like we've hit the perfect prescription here. I think we're good. And so let's try the other axis, make sure it's in both ways. Everything looks fine. And so it looks like our answer here is a -1. And so once we do our correction, it's a -1. Subtract your working distance. Always do that at the end. Don't try to do it in your head while you're doing it. Do it at the end. And our answer is a -250 sphere. Okay, another one. Up, we got against. It's really against. So we can't start with against. We had to have width. You'll just get confused. Step 1, you had to have with motion. So let's throw a -2. We still have against. This is no good. If you start here, you become confused. Optometrists, they start with negatives. They do everything different, but in ophthalmology, at least, this is how we do it. So let's throw a -4. Okay, finally, we have with motion. We can continue. Let's try the other axis. We can continue. Good. Now, and only now, can we start adding plus. So we go -3. It's a diopter stronger. And it looks like we've hit probably the perfect prescription here. Let's check the other axis. Make sure it's both ways. This patient doesn't have too much astigmatism. Nope. All right. Set your lens aside or leave it out, because if you put it back, you'll forget, you'll do the math in your head, you'll mess it up. And so what we have here is a -3 sphere, got the sign focus, you correct for your working distance, it's always a -150, and you end up with a -450 spherical power. So that's how you do basic retinoscopy. And so, what are the 3 steps? I'm going to hit you again with it. The 3 steps are you have to start with width, then you add power to neutralize the reflex, and at the very end, subtract a working distance to come up with your final prescription. So what about astigmatism? Now this has been pretty easy so far. If it was this easy, anyone could do it. It's not an issue. Let's look at another eye. Step 1, start with width. Good. We can proceed to step 2. Let's start